much energy is in a bond. It is a measure of the strength of a covalent bond. Covalent, we remember, are sharing electrons. We use Lewis structures to draw them out so we could see what things were actually bonded and how they were bonded. And remember the octet rule, that everything follows except for hydrogen, which is so small that it can only hold 2. When we break bonds, energy is required. So if energy is required, what would we call that process? Endothermic, absolutely. Good. So when we are breaking bonds, we are endothermic. Energy has to go into the system for the bonds to come apart. The opposite is true for when we form bonds. So our products are going to release energy. The bonds that are formed are going to release energy. So, exothermic, absolutely. It is exothermic. So, got to figure out how we're going to do it mathematically. We take the sum of the broken bonds and subtract from that the sum of the created bonds. The sum of the broken minus the sum of the created, which makes a lot of sense for us because we know that the created bonds are exothermic. We know exothermic is negative. It's releasing energy, so we mark it as negative. So we're going to subtract it. That way we don't have to worry about the negative part of it. The sum, yep. So you're taking the sum, you're adding up all of the bonds that are broken, and you're adding up all of the bonds that are created. Good question. The common bond enthalpies are given values. You will not have to come up with them. They're going to be given to you. They are in your data packet. If you want to double check my numbers as we go through notes today, you can get out your data packet so that you can see where I'm getting these values. But today for notes, I'm just going to give them to you. And it's a characteristic property, just like density is a characteristic property. Water at room temperature always has a density of 1 gram per milliliter. All of these bonds that we're going to look at, let's say it's a carbon-carbon double bond, that carbon-carbon double bond, no matter what else is attached to the other sides of the carbons, is always going to have the same bond enthalpy, the same energy in that bond. We often need to look at how the reactants are broken apart prior to how they are then put together. So we're going to look at both sides of the reaction. And again, Lewis structures are going to come in handy for you. So we want to predict the change in energy for the reaction when we take hydrogen and fluorine and we form hydrogen fluoride, or hydrofluoric acid is another word for that one. Are any of the elements that are on their own, hydrogen and or fluorine, diatomic? H is, absolutely. F is as well. Yep, so both the hydrogen and the fluorine are diatomic molecules. So I have H2 plus F2 forms HF. Is that balanced? No. What do I have to do to balance it? Add a 2 in front of the HF. Perfect. Perfect. Now I have a balanced reaction. So I have 1 mole of H2, 1 mole of F2, and 2 moles of HF. I'm going to look at my breaking bonds first because I'm doing broken minus formed. So I'll look at my broken ones first. And I have H2 and F2. Can hydrogen form double or triple bonds? No, hydrogen can only ever form single bonds. Because it already has one electron, it just needs one more. It'll always be a single bond. Fluorine is a halogen. Can halogens form double or triple bonds? They only need one more electron as well, just like hydrogen did. So the most that they can form is a single bond. They can't do more than that. There's no room for it. So both of these, if I were to draw them out, draw the Lewis structures of them, they'd be single bonds. So I look at my chart, and there's only going to be single bond information for these. An H bonded to an H, singly, which they always will be, has an energy value of 436 kilojoules per mole. Again, I'm getting that value from my data packet. So if you find a bond enthalpy page in your data packet and you look up HH single bond, it'll tell you that the value is 436 kilojoules per mole. What was that? Sorry. I'm going to be adding that to this one. It's actually just there. If you notice this plus that's up here, it's just the bullet points that this PowerPoint chose to use. It's silly, but we're going to say that it's because we're adding them. Works too. So a fluorine-fluorine single bond, if you take a look at that chart, should say that the bond enthalpy is 158 kilojoules per mole. Those are my only bonds that are breaking here. So I'm going to add those two values together, 436 plus 158, to get 594 kilojoules per mole of energy that is going into the system to break apart those bonds. I'm halfway there.
So those are the broken bonds, now we need to find the created bonds.
Exactly. Perfect. So the other half of it, my product, the stuff that is forming, I have 2 moles of HF. Both hydrogen and fluorine can only form a single bond, which is good because on our chart there's only an HF single bonded. I have 2 of them. So I'm going to have 2 times the value that's in my packet. My packet says I have a value of 566 kilojoules per mole. So I'm going to multiply that value by 2 because I have 2 moles of it. So 2 times 566 gives me 1,132 kilojoules per mole. And that's the only thing that I have on my product side. Those are the only bonds that are being formed. I'm only forming 2 of those HF bonds. So now I can take my data from the last slide and this data and put them together. So I'm going to take my broken minus my formed, so my thing from my last slide, minus what I just calculated, and I get negative 538 kilojoules per mole. So overall, my reaction is exothermic in nature. Even though there's energy going in to break bonds, there's more energy that is released as we are forming bonds, which makes it overall a net change of negative 538 kilojoules per mole. So it's releasing that much energy. Yeah. It should be